Hi, I think here we're going to get into a pretty important area, the adjuvant OCT techniques. This is going beyond pure structural imaging. This talk is an overview, and these techniques will increase the power of OCT. However, I'm going to go into why the stagnation that occurred, it took so long to get morbidity and mortality trials, why it puts a lot of these technologies on hold, which would be greatly enhance the current trials that are going on. So, Mark Brezinski, my background, most significantly, I, along with James Fujimoto, developed OCT. OCT had been around and was used in transparent tissue, and in the early 1990s, we got it to work in non-transparent tissue, and in a 7-year period, went from something that was not possible to um, in vivo imaging. So that's probably the most relevant accomplishment. Here's the list of the techniques I'm going to talk about here. The ones in white I'm going to speak about directly, so we'll get to those in other slides. So I'd like to just discuss the two in yellow. I'm not going to address imaging processing. I may do this in another presentation or have Dr. Aika Rogowska, who's done our imaging processing since the beginning, talk about it. I mean, one technique which she put forward is the sticks technique. I'd recommend reading about it, but there's so many imaging process, image processing approaches, edge detection, and she's the real expert. If you look at in my textbook, she wrote the chapter on image processing primarily, and so one of the only two chapters that I didn't write. Now, core length, assessing cores, I sort of put that in as an adjuvant technique, and I want to quickly mention it here. So, back in 2014, we began to wonder. We published that core length in the axial direction, not in cross section, um, puts patients at risk for rupture going to ACS. And that paper describes why we thought that given time. So long cores, more than 5 millimeters, we see them 30 millimeters long, um, associated with the TCFA, is more likely to lead in our assessment to acute coronary syndromes. And with papers published and people have noticed that plaques heal, which is what this is related to. So after the rupture, most plaques heal. And that's been noted with OCT for a while. But in a JAMA paper in like about March of 2019, we said that failed healing was the mechanism of ACS, not the rupture per se, and it likely holds for plaque erosion too. And then in the 2019 paper, which was derived, we had looked at our data previously. We had looked at um, a lot of histopathology with OCT images, special staining, and also analyzed a New England Journal of Medicine paper that was um, the primary paper describing angiogenesis in plaques, and came to the conclusion that angiogenesis is critical to plaque stability. And up until that time, our December 2019 paper, it was felt that it was detrimental. It caused um, bad things, and it actually stabilizes the plaque because it supports smooth muscle cells and endothelial cells, which can get into the clot and stabilize the clot. Now, how that relates to long cores is that these vessels can't go through necrotic cores. And again, don't use the term lipid cores because, as I described in the previous lecture, that can be almost anything. We're focused in on necrotic cores, but the vessels can't get through it. So if you've got a 5 millimeter or let's say 10 millimeter um, axial plaque, the vessels have to go over the top, but they reach a point where they can't go any further, and those areas have no blood supply, and so the um, they can't support smooth muscle cells and endothelium. And actually defining that length isn't easy. These things are all over the place. You have to know what parameters you're looking for, and I included it in core length, but again, it's been dealt with in previous presentations, and we're gonna go back to it again, but not in this talk. Now, again, that stagnation period, which was painful to go through, where we just weren't getting clinical, double-blind clinical trials. There was, anecdotal studies and, data thrown in from all over the world and collected together and making conclusions from it. And finally, we're getting to the point new investigators are on board. I'm grateful to them. And we're seeing double-blind clinical trials, which is what we should have had back in 2004. And why it took 15 years is a long story. But the problem was right around 2010, the NIH stopped supporting a lot of this extra work on OCT, like these adjuvant techniques. And so, and I discussed that previously, so some of them are basically halted. They haven't gone very far since around 2010. And they would be really powerful in these clinical trials. But they're just not going to be available for it. And so the trials hopefully will stimulate their production and them moving forward. Now, I'm not trying to be critical of anybody, but if you're not a clinician, you don't understand the concept, or most people don't understand the concept of clinical viability, what's important to a physician. And so to physicians, we don't always need precision data. So you don't need somebody's glucose 155.33333. It's not about precision, and this is going to become important in a lot of these technologies, because if you're not thinking like a clinician, you're just trying to make them more and more and more advanced. And what ends up happening is that they are less reliable, in my opinion. And I'm going to use an example like that in a minute. And first, those slides are out of order, sorry. So when we look at a chest x-ray, we don't look at densitometry. We're not looking for numerical data. This patient has obviously something in the abdomen ruptured. There's air under the diaphragms, and so we do a lot of qualitative stuff. This isn't about quantitation. So those two slides are out of order. I apologize. But if you had and we deal a lot with categorical data. So if you thought a lion at, let's say, 150 yards may or may not be charging at you. So the question is, what would you rather have, a radar gun or a pair of binoculars? Now, the radar gun is more sophisticated. It can give you velocity, but it's more prone to errors. You can miss. It can give you inaccurate data. But if you're looking through the binoculars, you see it, that the lion or the tiger is coming right at you. And this has been a problem with a lot of the adjuvant techniques. People have just pushed to make them more and more and more complicated. And I just don't see the reason why. So these are the ones that we're going to be focusing in on. I said we eliminated the other ones. And then the other part of it is in this clinical viability. First, it needs to be hypothesis-driven research. There was like this movement around 2000, to just engineer things and not do hypothesis-driven research. I am strongly against that. But it needs to be statistically valid, and there's so many papers, particularly ones that make claims about clinical um, viability, and you find them in optics journals because they need to be statistically valid. These are, you just need to do good basic or clinical science in with these techniques. So somebody could say, yes, we did this technique and we were the first one to do it in tissue. Well, if you don't validate it, it's not of any use. And we've been very big on doing hypothesis-driven work with validation. And so first I want to go to polarization sensitive OCT. So this is something we've looked at since the 90s. We've actually used it. It's a powerful tool. What it does is you're sending in polarized, I'm going to give you an analogy. You're sending in polarized light, and normal tissue isn't organized, so it's going to back reflect independent of the polarization state of the incident light. Whereas birefringent tissue, like organized collagen or organized nerve fibers that are parallel, they're going to be birefringent. The direction of the polarization is going to change the image. How you orient the polarization is going to change the image. Except we're the only group that works in what's called single channel PS-OCT because we tried dual channel. Dual channel gives you absolute numbers of polarization. So it will give you the birefringence in here. But first of all, you don't, we never found a point where we actually needed it. And secondly, it just increases the opportunity for errors. For instance, bending the optical fiber will change the polarization measurement. So will heating up the fiber. Whereas we look at a relative here, and this is from an in vivo study published in 2010. These are human joints. We ended up, it was an 2006 study. And if we look at the bottom left, you see those banding patterns. Okay, that's the polarization state, rotating as it's passing through the organized collagen. So this is cartilage in vivo in a human. And so because these were total knees, we actually got the histology from them when the knee was removed afterwards. So this one, we have a nice banding pattern. The orthopedic surgeons love them. They don't want numbers. And so, no, that's normal. Now, on the upper left, it says normal, but it's really sort of slightly abnormal. The collagen starting to get disorganized. And so this is early osteoarthritis, and I'm showing you cartilage just to illustrate the point. And then on the right, the collagen is just completely disorganized, and you've lost the birefringence. And back, if my eyes can read this slide, well, 2006, we showed this in coronary arteries. So if you look at the area with the green arrow, as we rotate the polarization in A and B, it doesn't change very much. And if we go to C, this is picroserous staining, which is for organized collagen. So the green arrow area in the histopathology shows disorganized collagen. And you can't tell that from the H and E in D. This is obviously a TCFA in D. But if we look at the red arrow in A and B, there was a dramatic change when we changed the polarization. And you can rotate this polarization really rapidly in vivo. So it's not like it's something difficult to do in the cath lab. And if you look at the bright green on C, that's organized collagen. So the green arrow is an area of disorganized collagen, and the red arrow is an area of organized collagen. So the area that's more susceptible to problems, it's the area with the green arrow. This technique has a lot of potential, but giving absolute numbers is not something I feel we really need. This is single channel. All we're doing is rotating the polarization. We don't care about the absolute value. We're just looking at the change at the time, at the way we rotate it. Hopefully that was clear. So OCT elastography, and first, elastography has been brought up with ultrasound in cardiology. It's used in the liver now pretty frequently. And you're basically applying two different pressures and imaging and looking how the image changes with the applied pressure. You actually have to do these little arrows are generated from cross correlation functions. But first of all, it's elastography, and it wasn't developed by us or anybody I know. 1991, OPIR. The citation is on the bottom. As far as I know, these are the fathers or the um, originators. I don't know if they're men or women of of elastography. And so, elastography, like PS-OCT, it's just a powerful technology. It tells you the composite. It tells you the tensile strength of the tissues. To be more specific, the elastic modulus, and we've studied this a lot up until 2010. Except now, in a paper, I had to publish this paper in somewhat of a throwaway journal because it was over 20 pages long. And as we were taking elastography to video rate, it started to become clear that there were problems associated with it. And also, it this paper talks about why it won't work with IVUS. Elastography won't work with IVUS. And this these two slides, sort of they're somewhat gross slides, illustrate the principle of why. So it's a great technique. We can use OCT with a parallel ultrasound beam or even an infusion of something. But so if we look first on the left, so if we were trying to tell somebody's temperature, but we used gradations like this on the order of tens. So could you distinguish between 99.8 and 102 with that meter? Not really. Accurately? No, not at all. And so here's where the problem comes in with a lot of the previous elastography studies, including ours, and using ultrasound. So you have to apply a pressure that's near the elastic modulus of the tissue. It's just like you need a thermometer that's roughly around 98.6, where there's a lot of gradations in that area. So when we calculated in that paper the force of an ultrasound beam, it was like 2 orders of magnitude too high by our assessment to get accurate measurements. But with OCT, even we needed to apply less pressures than we were applying. And the elastic modulus for normal coronary artery and diseased coronary arteries had been established previously. We didn't do that work, though we confirmed it. Now, the second problem, which was unanticipated, this was an abstract that was presented in Europe. I saw this just accidentally when I was going through papers, sitting at a Panera, and it was like an oh crap moment, because what this is when you apply a pressure to a tissue like an artery, what happens to, we all sort of assume the tissue changes instantaneously. And it turns out, if you're at 30 frames per second, the tissue does not hit steady state till roughly 1 frame. So most of the measurements you're taking, it's changing in a dynamic and unpredictable way. So so the elastography work at slow rates works well when you are not trying to do it at the speed you do it in a coronary artery. But when you're doing it with a coronary artery, you have to take into account that once you apply the pressure, you've got to wait at least one more frame to take the measurement. And we proposed in that paper the alternate frame technique. But elastography, so you're looking at two techniques. When we talked about areas that don't have angiogenesis, they're weak, structurally weak. Okay, they're going to be abnormal by PS-OCT and by elastography. Very powerful techniques. Doppler OCT, it's what it sounds like. Everybody who's listening to this knows what Doppler is. You do Doppler with OCT, you get it at a much higher resolution than you would with ultrasound. Here's an example paper. The Chen group has done a lot of work in this area. It's primarily used in the retina, but in spite of the fact we're interested in angiogenesis, I can't see, based on the speed, the movement, the varying directions of the vessels, it being practically used in the coronary artery. So we've pretty much written this off as, unless we have to come back to it because everything else fails, as a technique that's going to be important inside the coronary artery. Now, absorption spectroscopy is important. You'd think, well, we're sending in light, we can get the absorption spectrum because different tissue, let's say lipid versus water, has a different absorption spectrum. And the problem is scattering varies. And when you get the light back, it's a combination of the scattering and absorption. And the variation in scattering has pretty much made these techniques useless. So first, we weren't the first group to do this. I believe Joe Smith also did this early on. He may not have published it, but I've used his slide. He may have predated this group's on top, the Penn group, in doing dual wavelengths. So you do OCT at two different wavelengths, one where water absorbs, one where water doesn't absorb. And if scattering is constant, you can quantitate water. The problem in a coronary artery, scattering isn't even close to being constant. So we looked at group velocity dispersion. That's our paper in the next line. Well, if you go to the third paper, it is used, this dual wavelength technique, or these absorption techniques are useful in the eye, but as I point out many, many times, the eye is transparent tissue. It minimally scatters. It's not the same world as the coronary artery. But so we looked at in the middle group velocity dispersion, which is wavelength dependent dispersion. So when we send in an OCT beam, it's a bandwidth, it's a bunch of wavelengths. And not all wavelengths are affected the same way. So you get a distortion in the light reflected back. This is somewhat resilient to scattering, but but the problem is you get all the dispersion from the tissue above the area of interest. And we found a way, we believe, to overcome this, and we're going to get back to it. Now, this is an area we, as far as I know, pioneered it. It's an exciting area. It got knocked down by the NIH in this, okay, let's wait for morbidity and mortality data. But if you send in a phonon ultrasound, which you can make, you don't have to have a detector, so you can make a very small ultrasound transmitter on a catheter. It's just a little crystal. And what'll happen is when the phonon and photon interact in tissue, the interaction will be, the wavelength of the sound beam will be different depending on what tissue it's in. So it's going to have a different signature. So if the photon and the phonon interact in lipid versus when interacting in water-based tissue, it's going to send you back a different signal. So this is very promising, but it also works in two different ways. It's actually two techniques. So if you run the ultrasound beam parallel, then the beam goes to the side, and for reasons I'm not going to discuss, we published this in the proceedings, a Natural Academy of Sciences on top originally, but the next slide is going to show the interesting aspect of the paper. But it can be used to improve resolution because it removes something called multiple scattering. OCT depends on single scattering, so if you can get rid of multiple scattering or as much as you can, you improve the resolution. But if you use if the OCT beam and the ultrasound beam are perpendicular, then it'll give you tissue properties. I'm not going to go into that. We will do this in a whole separate talk, and for those interested, I'll discuss the physics. Now, I want us to point out that Lihong Wang does something acoustical optics, and that's very different. His work is great. I'm a big fan. What they do is they're, sending in light, and I don't want to oversimplify because he does a lot of different work, but they're sending in light and sound, and then looking at the scattering pattern and changes with the sound all the way around. It's not OCT, not even close. Now, what was exciting, this was their second paper. It was published in the Journal of the Optical Society of America on OCT with ultrasound, is that it works by the photoelectric effect. I do not expect you to understand the graphs above. The only thing I want you to understand is that they're not linear. So if you look at it as a function of frequency or intensity, you get what's similar to the photoelectric effect. It's a quantized phenomenon, and may not be very exciting to you, but it opens up the opportunity because it's quantized to really pin down tissue characteristics or to control the light waves. It's a very specific event, and so I managed to double paste the similar slides. Didn't want to, but that'll be fine. But if you look at the paper, this is the interaction of light and sound is very complicated, but the opportunities for characterizing tissue, and this can be made very simple. We're not talking about making this into a CT machine, is huge if you combine light and sound. And so hopefully with the reestablishment of the double-blind clinical trials, these things are going to get funded, and clinicians are going to be able to use them and say, oh, this is what I'm looking at, or gain more information from it. Now, groups, particularly this started with the group in BU, Tesh, and I just drew a blank, I apologize. They developed, you started to use entangled photons, which I'll explain on the next slide, and Salin is the other author. But unfortunately, this is a second order correlation technique. I know you don't understand what that means, but it's not OCT. It's a spectroscopic technique, quantum based. But the one thing it isn't, which is OCT, because OCT is a first order correlation technique. And unfortunately, it still bears the name of quantum OCT. And you see this all the time, and it somewhat drives me crazy. If this is quantum OCT, then anything that uses light is basically quantum OCT. So with OCT, you're using one detector when that light comes back, an interference into one detector. That's first order correlations. It's more accurately one channel. With second order correlations, you're correlating two different detectors, the coincidence counting between them. So this is not OCT. And the reality is second order correlations are removed from OCT systems as a noise source. And we're going to talk about that in a minute. Now, an entangled photon is one of the great mysteries of quantum mechanics. It's one of the areas where people just go, wow. So if I'm going to just put in a hypothetical um, question, case, and here this this image is from this paper, and the artist is listed on the slide. But if we look at the red and blue, they're two photons separated in space-time. But the little, you know, bubble around them is telling you that even though they're separated in our space-time, they're one entity. This is what entanglement is. It's unique to quantum physics. It's critical in the reality of the universe. I talk about it in the quantum complex biological systems um, lecture. It's in the paper on quantized OCT. But they are one unit. So if you do something to one, it affects the other, even if they're 10 light years apart. So that can be a very powerful tool. The problem is that these things are only produced in very extremely low intensities, these pairs. And it's attractive. It gives you not only reflection, the reflection from surfaces, but it gives you composition by measuring the group velocity dispersion in that region, unaffected by the region it passed through, just that region. So imagine this is a hypothetical and sort of going off um, pretty far, but imagine you sent one photon in the patient and kept one photon out, and you then did a measurement on the photon that was out of the patient. It would tell you the environment the photon in the patient is. I know that makes no sense, but that's quantum mechanics. I will, in other lectures, go into that in great detail. So I contributed the problem with the title of this paper. So I think, I don't know, this was 2018. I published this paper. It had been published in a shorter version in Arvix um, prior to this, but I derived the quantum field theory of OCT, and unfortunately I said part 1 first order correlation, and people took that to mean part 2 was going to be second order correlation, and second order correlations aren't OCT, so I contributed to this quantum OCT problem. But for those interested in reading about it, and I know it's not interventional cardiologist, I once was at an ACC meeting or an AHA meeting in Atlanta, and some interventional cardiologists came by at one of the restaurants, and I was reading, and they're like, "Oh, you doing OCT?" And I said, "No, I'm doing a quantum mechanics book," and their faces just went really negative and said, "Why the hell? Why would you want to do that?" Not in that quite so nice at terms, but yeah, to the interventional cardiologist, I'm sure this quantum stuff isn't very important. And these are two papers using entangled photons. And again, they're, as I butchered their names the first time around, Zell and Tech are two of the people who really pushed this forward early on. A more recent paper is below, but again, it's not going to be a practical, there's no evidence for it being practically used with OCT. But we came over it, and so I showed you that textbook that was in green by Shi, and she found that what are called thermal photons, and they're very common, and they're also in an OCT beam in the light that's being shined on you. They exhibit quantum second order correlation also. They can exhibit these entanglement-like processes, and these were being filtered out by the OCT system. But what they can give you is, again, information inside the tissue unaffected by the tissue that they pass through quantum mechanics. So we first published this concept in 2008, but it wasn't reduced to practicality. It was I patented it in 2016. But I do have the paper. We have run the studies on it. It does work. It's been delayed for a couple of years because you're going to be unfamiliar with this kind of concept in um, cardiology. But so what you do is you do a rough derivation from the quantum mechanics standpoint. You do your tests, it works out perfectly. But then when you go back to do the full derivation, you have extra terms. And you before you can publish, you've got to figure out why you got those, what happened to those extra terms that clearly aren't contributing and you didn't take into account for. And so that's where it sits right now. But it's very good at differentiating lipid versus water. And we're looking for necrotic cores which have lipid in them, and we want to differentiate them from hard plaques which don't have lipid from within the sample, but not being affected passing through the intima that gets before the core. Powerful technology. In some areas, could this replace OCT? Yes. Like the joint, also could it be used with OCT? Absolutely. In the study we're publishing, we did use it. We built a combination systems doing both simultaneously. These are all discussed in my textbook. And thank you for your time.